Hey, welcome back, students. In this video, I want to go ahead and show you how to calculate the moles that you should have gotten from the chemical reaction in the experiment that we ran. And so what I want to go ahead and do is kind of show you how to set up the grid here. Keep in mind that this is the equation that appeared on the Google Classroom site. Wherever you see a positive sign here in terms of the overall reaction, we want to go ahead and bring a line down. So I'll do that here, I'll do that here, and I'll do that here. And then we'll do the same thing here where the arrow is. And the reason we're doing this is because we want to go ahead and separate each of our columns by the number of compounds in the reaction. And we have a total of 5 compounds for this reaction, 2 on the reactant side, 3 on the product side. And so we want to go ahead and do that. Keep in mind that the overall conversion or the mole ratios overall for this particular problem are essentially going to be here a 1, 1, 1 all the way across. Okay, so I've already identified those in red, but we'll go ahead and separate this out one more time. We're going to put another row here, another row here, here, and here. Keep in mind from the previous discussion that the first row here was for grams. The second row was for molar mass. And if I take the grams and I divide it by the molar mass, that will equal the third row here, which is going to be the moles that we have. And then the following row is going to be the moles that you need. And then the last row here is going to be whether we have any excess. And I'll put a question mark on that. Okay, let me just fix up my rows here. But this is going to be the setup that we're going to use. I'm only going to provide here the information necessary for you to calculate trial number 1. And so you can use this information for the rest of trials 2, 3, and 4. And since there's only 4 of them, it's not a lot of work, but you should use this same pattern here to solve the ones for trial 2, 3, and 4. So here we go. In the very first problem, what we encountered was that we had a certain number of grams and for the sodium bicarbonate and for the acetic acid. And so if we go over here to the very first section of this particular one, we notice from the very first trial that for the first experiment for the sodium bicarbonate, we were provided a value of 1 gram. And for the acetic acid, we had to convert 0.5 grams into milliliters. But for this particular calculation, we don't have to do any conversion because it's already provided to us in a certain amount. So what we'll do is we'll take the amount here, which is going to be 0.5 grams, and so we'll go ahead and convert. Ideally, what we want to do is go down the list here, make our way downwards the list, and we first have to convert here. We have to get the molar mass so that we can get the moles, and we want to do this for both of these particular sections here. So I'm going to go ahead and erase this because I really don't need this on the screen, but we first have to figure out the molar mass of sodium bicarbonate, and then we have to figure out the mass of acetic acid. And so if we do that here, this is what we'll get. So what we'll do here is we'll go to the very top of our column. We'll do the very first one for sodium bicarbonate. And so what we'll do here is I'm just going to go ahead and estimate, but you should definitely use the most accurate numbers from the periodic table. But here we notice that sodium, that value in mass is 23. There's 1 for the hydrogen. There's 12 for the carbon, but when it comes to the oxygen, there's 3 of them. Each one has a mass of 16. That'll give us a total of 48. If I add all of these numbers up, these numbers are going to be equal to 84 approximately. So I'm going to use a little squiggly line like I did in class. So the molar mass of sodium bicarbonate is approximately 84 grams per mole. Okay, do a similar process here for the acetic acid over here on the second column. Let me put that in. I guess I can use a different color here. Let me use blue. And so if we do that here, there's 1 for the hydrogen, and there is going to be 2 carbon, so that's 12 times 2, that'll be 24. There's 3 hydrogens in this one, and then the oxygens here, 16 times 2 is going to be 32. If we add all of these numbers up, that will give us a mass approximately equal to 60. And so that number here goes down in the second column for molar mass in the second cell, so it's approximately 60 grams per mole. Okay, so you want to go ahead and do this. Now the grid is designed already in such a way that if you come in here and you start dividing the grams number divided by the molar mass, in other words, if I take the grams divided by the molar mass, that will give me the number in the third row, which is the mole number. Okay, and if I do that here, I'm going to go ahead and do that math for you. You should do this on your own calculator, but essentially you take the 1 gram and you divide that by 84. You should get approximately the following numbers. I'm going to go ahead and change my numbers here to yellow just so we can have consistent numbers all the way across in color. So the number here should be 0.0119, and these are going to be the moles, but these are the number of moles that I have for the sodium bicarbonate. If I do the same thing for the acetic acid, I'll take the 0.5, divide that by 60, and when I do, I'll get this number here, 0.00833, and of course that's going to be the moles of acetic acid. Okay, now for us to determine the number of moles that we need, we actually need to make sure that we do a little bit of dimensional analysis. I'll show that in a second, but we want to use the little shortcut method here. And so what you want to do here is you want to go ahead and do the following. And let me use in green. I'm going to go ahead and start with this number here. I'm going to multiply it by the coefficient of the compound I'm trying to find, divided by the coefficient of the compound that I start with, and that will give me the value of the other compound. Since I started with sodium bicarbonate, it'll give me the number of moles of acetic acid that I actually need in this particular problem here. And so what does that really look like done a different way? So if we do this, if I do the math, 0.0119 times 1 divided by 1 actually winds up giving me, and I'm going to put this in green here, 0.0119 moles. Go ahead and do it the other way here. Well, actually, before I can do that, let me go ahead and show you here what it's going to look like. I'm going to go ahead and erase something here. I'm going to erase this, do this here. I'm going to go ahead and erase this part down here just so I can make a little bit of room for myself for right now. Same thing over here on this row. All right, and so what we're going to do here is I'm going to show you the dimensional analysis. And so what will happen here is I'm going to go ahead and use this. I'm going to go ahead and start with the number of 0.0119 moles of sodium bicarbonate, and so Na, and so we'll put here NaHCO3, and based on this starting amount we got to figure out how much of the acetic acid do I need. But remember, the mole ratio, for every 1 mole of sodium bicarbonate that we use, we're going to need 1 mole of acetic acid. And so here's the number here. Notice the number that winds up happening here will cancel out the moles of sodium bicarbonate. That leaves us the moles of acetic acid. And so the final answer here is going to wind up being 0.0119 moles of the acetic acid, C2H3O2. And this is the number that we actually have there. Now, if you do the same process for the other way around, let me just go ahead and do this here. I'll circle this here like this. Times the 1 divided by 1 will give us the number on the other side. I'll go ahead and erase that. Okay? And so what we'll have here on this other one is 0.00833. Notice the units of moles. And now we're in a position to figure out here at the very bottom whether we have excess. And so which ones of the two is excess? Well, in order to solve that, all you need to do is take the moles that you have and subtract the moles that you need. Since it's already set up quite beautifully here, we're going to take this number, subtract this number, and that'll tell us down here at the bottom whether we have a excess or not. Essentially, excess is going to be represented by a positive number, negative is going to be represented by a, limiting is going to be represented by a negative number. And so let me clear a little bit of space for us because it's a little bit crowded on here, so I'm going to go ahead and erase this. If I can here, let me see. Do this, erase this at the bottom just to make a little bit of room. If you need to see this again, go ahead and rewind it on your viewer here and you can see what was there before. But let's go ahead and do the math now. The very bottom, what we'll do is if I take 0.0119 and I subtract the 0.0083, what we wind up here is going to be a positive number. What this means here, it's going to be excess. Now, if the problem asks you how much excess, well, you just do the math here, and the math actually says that you should have 0.0036 moles of excess. And it's going to be very specific, moles of excess of the sodium bicarbonate. Okay? Now, which one's the limiting? Well, let's do the next one here. If I take 0.00833 and I subtract 0.0119, that will give us a negative number. The negative number here tells us that this here is going to be the limiting number. And it doesn't matter what the number is, because as soon as you have a negative number, that tells you you ran out. Okay, so what the negative number here tells us is this is the one that runs out first. Okay, so the limiting reactant in this particular case is this one here. So we look at the moles that I have using this number. That's how we'll get to the other side, and we need to get to this section over here because we don't know that, the number of moles of carbon dioxide produced. This is going to be the amount that we expect to get. So if I take this 0.00833 from the limiting reactant, I multiply it by 1, I divide by 1, that will give me the unit that I want over here on this other side. Okay, so let me clear these arrows out of the way. And if I do that, the number that I wind up getting over here at the very end is going to wind up being 0.00833 moles. This is the amount of carbon dioxide that I expected to get. And so you want to use this number and compare it to the moles that you calculated from the milliliters of gas captured in the previous video. And if the difference is very small, in other words, if the number is very close, then that means that you had a very high percent yield. So you did everything very close to perfect. But if the number is very different, here's where we start to see whether your percent yield was actually pretty good. And so in the next video, I'll go ahead and show you how to get the percent yield. And ideally, what we want to get is a percent yield in the 90s. If we don't get that, then we need to start looking at why we did not get the high percent yield. Why did we not get what we expected? And so at the end of the day, it's not terribly crucial or wrong that you didn't get the right percent yield, but you should be in a position to explain why you did not get that percent or the result that you were expecting to get. Okay, so hopefully that was helpful. If you have any questions, go ahead and see me in class. I will be back on Monday, but this hopefully will be the first example that you can use for trial 1. Just use this for trial 2, 3, and 4 in terms of determining what the expected moles of carbon dioxide are going to be. Keep in mind that you must identify what the limiting reactant is first before you can start using the crossover over into the product side. Okay, I'll talk to you soon. Bye-bye.